This is the fourth in a series of gas calculations. This particular one involves the changing of two of the three gas variables at the same time, and that clearly is a new situation. If you look at this one, you'll see that on the left we have a pressure of 10 and a particular volume, and the particles are moving at a certain velocity. On the right, the heat's been turned on, so the temperature is up, but the pressure is also up. So calculating the volume will be dependent upon two factors. So let's look at an example. Here we have initial volume of 2 liters. You're given the initial temperature, pressure, the final temperature, the final pressure, and the unknown is the final volume. And again, it's recommended that you identify and write the variables out as part of your solution. As always, since we're looking for V2, we start with V1. And then we're going to use a fraction, and we're going to begin with the temperatures, and we'll use the top heavy with the 400 on top, because if the temperature goes up, the volume is going up. And so we put the 400 over the 295, and then we're going to put the 1 atmosphere over top of the 2 atmospheres. Because the pressure has gone up, that would mean that the volume would be reduced, and we end up with a final answer of 1.36 liters. And it happens to make sense, because the pressure change is twice that, whereas the temperature only went up by 1/3. And so as a percent of the original values, the pressure change had a greater influence. Another example involves looking for a final temperature. Here we have the volume reduced and the pressure reduced. So we do the same thing. Since we're looking for T2, we start with T1. And then we're going to use the 2.5 over the 4 liters, because if the volume decreased, clearly the temperature must have decreased. So we use the so-called bottom heavy fraction. And the same is true for pressures, because a pressure of 1.5 atmospheres is caused by slower moving particles than 2. And we end up with a final value of 138 kelvins. And again, the final value makes sense. The volume went down, the molecules must have slowed down, and a decrease in pressure will cause the molecules to be occupying less space. We have, at the end of all this, something called the combined gas law. You will remember that volume is proportional to temperature, and pressure is proportional to the 1 over the volume. Well, it turns out when you all combine them, you come up with the fact that pressure times volume over temperature is proportional to the moles of gas, because in all of our examples so far, we have not changed the amount of gas. And this is known as the combined gas law.